Okay, everybody. I know people are still kind of working their way back in after break, but we should get started. Just a little process. We're going to have 2 talks, and then we're going to have a small break while they reset the stage for the panel. Okay? So I'm very pleased to say that our next speaker is Dave Clark, who's a senior research scientist at MIT, Computer Science and Artificial Intelligence Laboratory. He played key roles in the development of the Internet and its architecture and protocols. He chaired the Internet Activity Board. He programmed the protocol suite for Multics, Xerox Alto, and the IBM PC. And he's going to be talking about the early history of networking. Everyone, please welcome Dave Clark.
Yeah. One of the consequences of being late in the day is that I've changed the slides 12 times since I started. And this may be a little incoherent, but I tried to decide how to talk about the history of networking, and I decided that we've had a transition in the problem we didn't know how to solve from the early problems, which I would describe as pragmatic and mechanical, and later issues are more fundamental. And I realized it's sort of like raising a kid. When you have a 2-year-old, every day is a little disaster. And when you have a teenager, the disasters don't happen very often, but when they do, they're cosmic. And I decided I'd go back to the early days of the Internet, or the early days of protocols, because that history is more lost. And it really reminds us, I started to say how thoroughly we didn't know what we were doing. That's slightly harsh. How thoroughly we didn't know how to do what we were trying to do. So I want to talk about some of these perhaps pragmatic and mechanical issues, and they really had to do with how to structure the code, how to position the code within the system, and of course, performance. So I want to explain what I meant by structure. There are some distinctive features about network code, and I want to start there. So I'm trying very hard not to give a talk about networking, but I'm going to look at networking for a few slides and then talk about the implications of that for the operating system. So I actually wrote my PhD on I/O. Jerry Saltzer said to me, because at the time we were certifying Multics as a multi-level secure system, we're trying to throw everything out of the kernel. And he said, okay, for your PhD, throw the I/O system out of the kernel. Well, okay, but we didn't want to have to audit all that code. And I got all of the I/O system out of the kernel except networking. And I realized there was something funny about networking. Networking was not I/O. And these are sort of like obvious things, except back then we had to learn them one at a time. The first is when you read a page from the disk, you know how big it is. And when you read a record from the tape, you usually know how big it is. But when you decide to read from the network, first of all, you don't know how big the packet is, and then you don't know how many packets you're going to get before you have something to give to the application. The next thing you have to learn is that everything you get is potentially broken. The packets are malformed in every possible way. Now we call it an attack. Then they called it a bug. But you can't write networking code in a strongly typed language, because almost everything you do is you got this bag of bits, and you're looking at it a field at a time, saying, is that a valid field? And then you can say, OK, treat that as an integer. Call it an integer. But this actually adds amazingly to the bulk of the code. The second issue, or the third, 1, 2, 3. The third issue is these machines are heterogeneous. I was programming on Multics. It was a 36-bit machine with 9-bit bytes. And TCP was defined in terms of 32-bit fields because they were thinking about a 30. I can't tell you how stupid code I wrote converting 9-bit bytes to 8-bit bytes. And byte order, let's not talk about the formats of floating point numbers. And the other issue is you don't know what's going to happen next. When you read from the disk, you have some sense of how long it's going to be, but you can say, OK, software, read a packet. Nothing comes for a half hour. And it was the time scales of the asynchrony here were very confusing. And the other thing, which was absolutely why I couldn't get the networking code out of the kernel of Multics, is you have to process the packet to see who it's for. Now, on a personal computer, it's who cares? But Multics was not only multi-user, it was multi-level secure. So you needed to do all that demultiplexing in a trustworthy space, which meant ring 0 to speak Multics at you for a minute. So I went back and I found a slide. I was trying to figure out, I'm drawing shamelessly on my own work, because I wanted to illustrate some early slides, and the only ones I could find were mine. And so I found this slide from 1986. And of course, we standardized TCP and IP in 1981. We were coding it in 77, 78, 79. And this is sort of how I felt about it in 1986. And I said some general observations about protocols. They're difficult to understand in code. We thought that was true at the time. The implementations are often very large. That was true. And they don't perform very well. And this is sort of dismal. And down there I said, what's the cause of this? And the first one is, well, maybe we as protocol designers screwed up and we didn't know how to do it. And we were designing stupid protocols. The second one is, they were great protocols, but we didn't know how to code them. And then I said something else, question mark, and I didn't put the rest of the slides from the talk, but actually what I was hinting at is a very poor match between the implementation environment in which we had to write this stuff, the operating system, and what we assumed it was going to do. And we had to batter our way through this, and moving from specification to implementation was actually, we just didn't know how to do it. I wrote down here, and I'm sort of reconstructing this from ancient history. I didn't put a slide up here, but in programming a protocol, what was the hard part of the problem? TCP has states. It's either an established state or SYN wait or all these kinds. Early on, people said, oh my God, it's so hard to build a state machine. I'm going to build a whole new language to have otherwise it's this huge incomprehensible case statement. No, it wasn't hard to program. There was actually just marshalling the packet fields, as I said, getting these bits in and deciding whether they were protocols or not. Dealing with errors. Barbara, I think, talked about this issue in the distributed system, that it was nice if your computer stayed up when that one crashed. If you were willing to go down when they did, we called this fate sharing. You know, if you die, I'll die too. It made it so much easier to write the code. I figured out that if you wrote a protocol under the assumption that the other guy always did the right thing, you stripped out about half the code. And the error checking code was the hard stuff because the errors were so inexplicable. And as I say, today we call it an attack, okay? Sequence numbers in TCP were 32 bits, but mod 32, they could wrap. There are people who said, how could you possibly give me 32-bit, mod 32-bit numbers? I have to ask which one's bigger than the other mod 32 when I have a 16-bit machine. Get over it, okay, just code it. We finally figured out that copying the data was extremely costly, and therefore we had to do that very efficiently. And then we figured out what the real problem was. And in fact, this is today where most of the instructions are in processing TCP, which was the rate adaptation algorithms to deal with congestion control. Had nothing to do with the packet at all. And then, of course, there's dispatching the packet to the direct connection. If you get an incoming packet, you have to look up in some table to see who it belongs to. If you have a personal computer and there are 3 connections, no problem. We said to ourselves, but someday there'll be servers. They might have 1,000 connections. And we were anticipating the web. And we suddenly realized that was probably the most costly step. Of course, now in very specialized systems like routers, for every packet, you do a longest prefix match of the IP address against a table that's got 400,000 entries in it. Okay. Believe it, that takes a special algorithm. And then dealing with layers. I'll come back to layers in a minute. I want to talk about layers. But here's a picture I had from that same talk. We didn't know where to put the software. Now, you're going to see echoes in this picture in very pragmatic terms of some of the stuff you heard about today. We heard about events versus threads. We heard of Lauer and Needham's duality. We were dealing with exactly the same question. Where do you put the protocols? One answer is, well, the user is trying to do something, so put the protocol in the environment of the user. That was this circle right here. Okay? It's easy to invoke. You just call a subroutine, but there's no asynchrony. You could, if you put the protocol down in the operating system, which is where at least some of it had to be because you had to do trustworthy dispatch, it was a low overhead to execute the code, but it was a nasty programming environment. You were missing some features down there, like in some of these early systems, you couldn't create a process inside the kernel. Okay. And of course, what you ended up doing was running all the code at interrupt time, which of course is sort of like this conversation we were having earlier about events versus threads. Why don't you just run the code? And I'm going to come back to that. And then the other idea was, well, why don't you just create a process and put the protocols in the process? That's really convenient because now all the state variables are in the process and you don't have to do any locking, okay? Because it's just a process and it's running single thread. And the problem with that is you have a very odd scheduling problem when we do networking. And, oh, that button. This is very strange. Because as I said, you don't know when the next packet's going to come. So protocols at the time did something that seemed odd at the time, which is, let's say you're TCP and you're running along and you get all done. You say, I'm done, I'm going to wait. But you don't know what you're waiting for. The user could send you I want to send some more data. Or some more data could come from the network. Or a packet you've sent has failed to receive an acknowledgement and your timer went off. So you're waiting for at least 3 events. And some of the early scheduling primitives, block and wake up, P and V, sort of implicitly assumed that you knew what you were waiting for. And that process that I drew you over in that previous picture, what's it waiting for? Well, it might be waiting for something to come from here. It might be waiting for something to come from here. It might be waiting for a timer. That was actually hard to code. And furthermore, when the code woke up, it had absolutely no idea what had happened. Its whole world had changed around. It had, where am I? What am I supposed to do? It didn't know what it was doing. It was hard to think through how to code that stuff. So there we go. Thank you. So I had a picture earlier of sort of structural questions. This is the cost question. And this question of the duality that, we were hearing about earlier of Lauer and Needham. Barbara said it's not clear that they were dual with respect to performance. No. No. We had to learn the relative cost of different actions, and we didn't know within a factor of 10 what that was. How much did it cost to process the header of a packet? How much did it cost to schedule a thread? How much did it cost to set a timer? How much did it cost to take an interrupt? How much did it take to copy the packet or dispatch the packet? We didn't know. We started out thinking that the protocol processing was the expensive step, that it took a lot of cycles. I don't want to say that. I don't want to say that yet. It turned out processing the header was the cheapest task you could do. Now, I implemented the first TCP in Multics, and it took 25 milliseconds to schedule a process, and so I wrote a threads packet. It took 4 milliseconds to schedule a thread. And I felt that I was sort of fighting the structure of the operating system. And the next thing I did was we got some Xerox Altos, and I looked at the code there, which was the pup code from there. And it was gloriously simple. It was beautifully clean. And of course, it was written by smart people, and it was coded by smart people. I wrote the TCP by basically just looking at the pup code and then taking out pup and putting in TCP. And I wanted to show, OK. Thank you. I'm really disappointed because this scanned very nicely, and then I put it here, and it turned into Gluck. But for those of you who remember the visual effect of BCPL, that's a page of BCPL. This is the implementation of the TCP input routine for the Xerox Alto. And it fit on one page. Now, of course, I'm lying desperately because it called subroutines. But why is it doing this? Stop it. But the reason that this code was clean was that, of course, the code from Xerox, which is Ed Taft and Dave Boggs, was very clean. And I said, oh, protocol processing is simple if you're writing it in a machine which was in some sense born networked, like the Alto. It was also a personal computer. You didn't have to worry about secure dispatching. You didn't have sort of kernel protection. And I'm doing something stupid, but I'll figure out what it is done. I mentioned layers earlier, and we've layered protocols. I learned this from Barbara, right? It's layers of abstraction. Ah, yes, so we'll make the protocols, we'll layer it. Each layer of the protocol, there's the transport protocol abstraction, and there's the remote login. So how do you structure the layers? Well, we, at this point, were listening to a subthread through the operating system community of microkernels and lots of processes. So there was an obvious idea. Why don't you put each layer in a process? I say the idea was obvious but bad. And the reason I say this was it took much longer to schedule a process than to process a packet. And I said, but the specification is written in layers. It was actually Dave Tenenhaus who said to me, because he'd been involved in the OSI community, which of course had 7 layers, and he said, layering wasn't a strategy to modularize the implementation. It was a strategy to modularize the design committees. Why do you think that's not a thing. I laughed too, but it's not funny. And he said, why do you think the specification tells you anything about how you would implement it? I said, ugh. Okay. So the next thing that happened to me is I took a sabbatical. Thank you, Andrew Herbert. I went over to Cambridge. I shared an office with him. And I looked at the networking code they'd written for the operating system they had there called Tripos. Tripos was a beautiful, I guess it's still around in some branding. It was a beautiful little operating system, used processes for most system functions. A microkernel philosophy. Very efficient inter-process communication. You know, it was shared memory. You just passed a pointer. And I looked at their networking code. It wasn't TCP. They had a much simpler protocol suite. Beautiful, the TCP equivalent, the virtual circuit thing was a 4-page spec. And there was sort of 3 important layers, the network management layer, the transport, and then we were running remote login. And I looked at the code. You think about that TCP code where I could see the input processing in one page. I read the code that they had for networking. I couldn't find the networking code. And I was scanning through the listing. I said, well, where's it process the packet? Where's it process? I couldn't find it. And I finally realized that 90% of the code, and that's by count, was dealing with inter-process scheduling. And the protocol was 2 or 3 lines stuck here. I was missing it when I read the listing. And I couldn't figure out what was going on. Well, this is what was going on. They had 3 processes. They had the remote login thing. They had the virtual circuit process. They had the network process. There's a device driver down there. I'm sorry, my slides don't scan very well. And the picture over here is a picture of packet exchange. And the stuff over here was the terminal side, and the stuff over here was the computer that had the screen editor. We're doing character at a time remote login here. Think Emacs for those of you who remember that. And the lines going back and forth are packets. And so I type a character. The goal is to get the character to the screen editor, and the screen editor is going to echo the character. So you can say, well, why can't there be 2 packets? I drew that down here, packet coming over, packet coming back. But there are all these funny interactions going on down here. I send a packet across. I hand it to the login layer. I hand it to the virtual circuit layer, which sends a packet. The virtual circuit layer over here sends an ACK. Well, it doesn't have to send an ACK. It could do this. It could say, why don't we get all the layers together and have a huddle and decide whether there's anything we want to send back. And then after we've decided that, we'll send it back. And of course, there's always a final ACK. Well, the reason is it's much cheaper to send a packet than to schedule a process. You can't get these layers together to huddle because they're in different processes. And by count, although I don't remember the number, it was either 52 or 54, there were essentially 54 process wake-ups just to exchange a character. And I rewrote the code so that instead of being written as processes talking to each other, it was in one language which would be called an event, which is to say, when you get the packet, process it. Okay. And the code was 10 times smaller and 10 times faster. And I said, okay, structure matters. So got a couple papers out of this. One was a paper I wrote called The Structure of Systems Using Upcalls. Barbara had a picture today from, I guess it was Birrell and Nelson, which was remote procedure call. And if you looked at it really closely, when the packet came in, it went through several layers, and her picture just had an arrow between the layers. What's that arrow? Is it a process call or a subroutine call? Okay, like that's a factor of 10 in performance. So I made this proposition that maybe we should structure protocols not with each process, each layer being a process, but each kind of action. An outgoing packet, I wrote this slide in, I guess, 25 years ago, and it's an error. That arrow's upside down. That's the first time I've noticed that. You have to give a talk to find the bug in your slide. So anyway, imagine that arrow points down. You know, you start from the application. The application would say, hey, I want to send a packet, and you go down through the layers. That's sort of straightforward. But when an incoming packet occurs, you just call up through the layers until you've done all the stuff you can, and then you schedule the user process. And there's an interrupt handler over here. Now, the problem with this, not if you have an Alto, it's just code, but if you have a secure kernel, a multi-layer, is you're actually making a subroutine call out of the kernel into user space. And my illustration of the bad thing that could happen was you do the up call, and then the user code blows up, right, which I illustrated with the word blam. And how do you recover that? Because you probably have state on the stack of some process that's running in the kernel, which you now have to salvage. Okay, ugly mess. Okay, but I was trying to get at efficiency. I thought I'd mention another performance problem we had. It took longer to set a timer. Every time you send a packet, you have to set a timer because it might not get an ACK. It took longer to set a timer than it did to send a packet, which of course is why in this picture it was better to just send the ACK right then. Don't, because you'd have to set a timer to protect yourself. No, just don't do it. So anyway, there was this wonderful paper by George Varghese and Tony Lauk, which came up with a strategy for doing high-performance timers. Little things like this changed the performance of the things we were trying to build. And I went through an exercise. People said, protocols are expensive to code. I said, no, they're cheap. They're expensive to code. So I had a grad student, a student named John Romke, and I said, let's actually count the instructions in a TCP. So he compiled it. He gave me the assembler code. He said, you count them. You have the PhD. and I counted the instructions. And to receive a TCP packet, if you were the sender of the data, if you think about what that means, you're getting the ACK. It took around 200 instructions. It was actually more expensive to receive the ACK than to receive the data. Why? Because you had to run the congestion control adaptation code then. To set a timer using George's and Tony's scheme, 35 instructions. To process the internet protocol, 60. Cheap, cheap, cheap. No cost to this stuff, okay? Now, I have skipped in this brief run-through of the whole world here a whole range of topics, and I just thought I'd mention them. I basically talked about this issue of performance and network software design. One thing we did notice is that the network sort of wrung some of the heterogeneity out of the world. People stopped building 9-bit bytes because it was just too much of a pain. There's a thread I could have talked about here. It's been a thread which is going on for decades, which is to say that the protocol processing is so complicated that maybe I have to do this on a coprocessor. And what you do with a code processor, of course, is after you've built the coprocessor, then you build a protocol to talk to the coprocessor, and you discover that's just as expensive as the code you were trying to do. And it took decades to figure out the right thing to do. What we're doing today is you build a great big packet, and you hand the packet to the processor card out there, and then it breaks it up into little packets. Okay, but you know, it's how many cycles did it take to figure out how to build a fast graphics accelerator? Anyway, I learned my networking from big machines, Multics. The Xerox folks, of course, were dealing with small machines, entirely different set of issues. But they have to interoperate, okay? So the point is one protocol, one specification, multiple implementation strategies. And of course, now we're going to Internet of Things. You know, we're trying to put these protocols. I'm not saying you should use TCP, but it's got to fit in a machine, you know, that's got cheap, okay? TCP can fit in that machine because we can run TCP in anything. The question is whether you want to and how it would be structured. Stop it. Networks, as we designed them, were inherently serial. And the first time we realized we were in trouble is when I tried to hook the internet to a Cray. And said, that's a vector machine. And then we had machines that were really parallel, and the data coming in had to be fanned out somehow. And of course, the fan out turned out to be the most expensive thing we had to deal with. Of course, now we're dealing with multi-core machines. The TCP is probably running on one core. You've got to move the data across. It's probably highly inefficient. Maybe we should have built a parallel network. But somebody said, well, actually, you can't do that because my parallelism on my side doesn't look anything like your parallelism on your side. The only intermediate state is serialized. That's sort of a performance problem. I want to come back to network semantics. I'm going to put that on the next slide. This is following up on something that Ken said. I skipped some of the more recent issues here. As I said, this is the networking as teenagers. When you realize that your computer is hooked to the whole world, it changes your whole mindset about what your system should do. I used to turn my PC off when I wasn't using it because it was a personal computer, right? And the issues of security and availability and so forth that arise, this is what I meant, like once you have teenagers, the disasters are infrequent but catastrophic. And then, since Andrew talked about virtual computers, I would simply say that we have a concept of virtual networking, we have a concept of virtual computers, and I still don't know whether you need to hook your virtual computer to your virtual network or you want to hook the virtual computer to the real network and the real network to your virtual computer. We're completely confused here. We just don't know. And finally, since everybody's talked about how much better everything gets, you know, damn, speed of light is not on a Moore's law curve. It doesn't even get 10% faster over 10 years. The United States is 100 milliseconds wide round trip. and it's still going to be 100 milliseconds. Think how many instructions you can execute in 100 milliseconds. That's why RPC across the network became less and less and less suitable, and why people kept trying to do things that were less and less serialized or synchronized, and more, I'm going to send 100 messages, and then 99 will get lost, and so forth. We fight the speed of light as an immutable number. Okay. But let me put up a last slide here, because I've got to stop. I can see, yes, right, I definitely have to stop. I want to talk about this recurring structural issue. Networks, as a network thing, have a distinct set of issues they have to solve. The most obvious one being resource allocation. How much capacity do you get? How much capacity do I get? How do we deal with congestion? The network has some share of its responsibility for security. We need to know what it is that you're delivering. Am I delivering things to computers? Or am I trying to address a service? Or am I doing information-centric networking? But the key issue about networks as we design them is they don't know what they're being used for. Okay, this is the end-to-end model. Now, of course, this was a natural way for us to think, since we were computer people and we knew that computers were designed without knowing what they were used for. Ken pointed out that TCP isn't really suited for anything. But it persists because we couldn't find any other general model that was general enough that was worth putting into the core. The alternative is to push to the app the implementation of the desired semantics. And of course, we gave you a way to do it. It was called UDP. But if you push the protocol to the app, then the designer is implementing the protocol. Go back to the earlier part of the talk when we say we don't know how to do that, because do you put it in threads? Do you do it in processes? At least if the system has done TCP for you, it's done, and you have a straightforward interface. So the question is a protocol like transport a core service? And we were talking earlier about what's in the core, right? This is made more complicated by the final statement I'll make. Okay, this is a space in which nobody can count on anything, right? The net cannot trust the host. The operating system can't trust the app. The app can't trust any of them. But in some, we want the resulting system to have some reliability. Well, classically, we build systems that are better than the sum of their parts. At least we know how to do that for things like bridges, okay? But we really don't know how to build systems that are better than the sum of their parts in this space, because we haven't got the structure right yet, and we're still working on it. So that's the summary of why structure is a recurring problem here. I'm clearly out of time. I'm done.
Would anyone like to ask Dave a question? Let's see. It's hard to see from up here, huh? No?
Oh, come on. 3, 2, 1. Okay.
End of the day syndrome. Dave, thank you very much. This is our operating principle PAL shirts.
Thank you so much.
Thank you.
Yeah.